Hello. In this video, I want to introduce the concept of torque and how it is applied to rotational motion problems. So I've got this object here. This is kind of like a potato, but some arbitrary object in space. I've got some point here, the axis of rotation of this object. Often this will be the center of mass, but doesn't have to be. I'm going to write often is the CM. Doesn't have to be. I could fix this at some location that wasn't the center of mass, about an axle, say. And then let's say I apply a force. So I apply a force maybe out here. I apply some force on this object that looks like that. That force is going to cause some rotation. So it may cause the object to accelerate if the object isn't fixed in place. But it's also going to cause some rotation if it's applied in this way where you can kind of see it pulling around that axis of rotation. And torque is a measure of how much rotational force we're getting. It's not force exactly, but it's analogous to force. We define torque this way through a cross product. Torque, tau, is equal to R cross F. So R here represents the position vector between the axis of rotation and where the force is applied. So to write this all out, this is the applied force. This is the position vector from axis of rotation to the force of rotation to force. And then that tau, this is a tau. This is torque. These are vector quantities, and we're going to talk about the interpretation of them as vector quantities shortly. The first couple of things I want to say is a few points of interpretation here. So torque is rotational force, and I'll put force in quotes because it's not actually force. The way you know it's not force is by looking at the units. So the units of torque, the units here are, well, there's a position vector, so that has units, say meters, distance units, and some force units here. So it's going to be some distance units times force units. So the units are going to be meters times newtons, or I'll write that as Newton times meters. One thing to notice, I'll put a star by this too because it's important to notice it. This has the same units as energy or work. And one trap to fall into is to think that these quantities are the same because the units are the same. But the interpretation of work or energy is very, very different than the interpretation of torque. And so this is one moment when problems cannot be solved by unit analysis alone. You need to know a little bit of physics other than the units in order to figure out what's going on with torque problems. So that's one thing to mention here. The other thing that's important to mention here is that in the same way that net force will cause acceleration, net torque will cause angular acceleration. And we'll see that a lot. And so there's this whole analogy between linear motion, F equals ma, and rotational motion, torque equals I alpha. I'm going to write down this expression, and we'll talk about it more fully as we go, or in more detail as we go. But this is saying that torque is proportional to angular acceleration. So this is angular acceleration. We've seen that a little bit before, but not much. The units of which are radians per second squared. So how much angle per second per second. So that's an acceleration in angle. And this is the torque again. This quantity, you'll notice here, if this were F equals ma, and torque is analogous to force, and angular acceleration is analogous to acceleration, then this quantity I is analogous to mass. This is the thing that tells you how resistant a certain object is to angular acceleration. So it is a measure of inertia too, but just inertia in the rotational context. So this is actually called rotational inertia, or most commonly the moment of inertia. So this is basically rotational mass, and I'll put mass in quotes. And the units of this, you'll notice, are, well, if torque has units of newtons times meters, and this has units of radians per second squared, it turns out, and you can work this out on your own, that this quantity, the moment of inertia, has the units kilogram times meters squared. Kind of weird units. We'll talk through the interpretation of that in a bit. But one thing to start with here is to say that the mass matters. Something that's more massive will be harder to rotate. But also, there's something about the dimensionality of the, or not the dimensionality, but the size of the object. Something about this is indicating that the size of the object matters, or the shape of it, perhaps. And so we'll interpret this more fully as we go. But the key point for the purposes of this video is that torque causes angular acceleration, net torque. And so I'll write torque net here in the same way that net force causes acceleration. Okay, the third point that's important is that while net force causes acceleration of the center of mass, net torque causes rotation about the center of mass. And so in general, where we're going with this is we're going to be studying this because we're going to try to decompose the motion of any object into motion of the center of mass and then rotation of the body about the center of mass. And so this sort of analysis is leading us towards a complete description of the motion of any object, both its translational motion and its rotational motion. Okay, so those are kind of key interpretive points about torque and its meaning and what we're using it for. I want to show a quick example here of how to think about what torque is doing. So if I have a rod, let's say, or a stick, if you like, here's a stick, and I fix that stick so that it rotates right about its center. And I apply 3 forces to it. So let's say I've got one force that looks like this, and I'm drawing these forces at the point where they are applied, because that is an important thing to know for these sorts of problems. There's another force F2 here, and another force F3 here. All these forces have the same magnitude, let's say. So I've got, let me just stipulate that the magnitude of F1 equals the magnitude of F2 equals the magnitude of F3. Not all of these forces, so all the magnitudes of the forces are the same, but they don't cause the same torque. And the reason why they don't cause the same torque is because they're pulling in different directions. You can see that you might have an intuitive feel for this. So if you take a look at F1, F1 is pulling down. So it's kind of intuitive to see that we're going to get some rotation that's going to start going clockwise around this axis of rotation right here. F2, similarly, we've got some pull that's kind of causing clockwise motion. F3, however, is just pulling straight out from the axis of rotation. And so we're not going to get any rotation at all. All F3 is doing is really pulling on that axis. If this wasn't fixed in place, this would just cause a translational acceleration to the right. If it is fixed in place, this force really doesn't do anything. Maybe it puts some stress on this axle, but it's not causing any rotation. The way that we can quantify this is by going back to our definition of torque. So torque, this cross product. In all the cases here, the r vector is the same. So I've got r is that vector from the axis of rotation to where the force is applied. And in this case, all the forces are applied at the same place. So I'm just drawing one r vector for all three of them. If we want to figure out what the magnitude of the torque is, then there's this way of representing the magnitude of any cross product, which is to say the magnitude of the torque will be the magnitude of the position vector times the magnitude of the force times the sine of the angle between those two vectors. So theta in this context represents the angle between the position vector and the force vector. So what that would look like in the case of F1, r points this way, F points this way, so the angle between them is 90 degrees. In the case of F2, R points this way, F2 points that way, so the angle between them would be something less than 90 degrees, maybe about 45 degrees in this case. In the case of F3, R points to the right, F3 also points to the right. So they lay right on top of each other directionally. So that angle is 0. And so if you look at how the sine function works, F3 is not going to get any torque because sine of 0 is 0. F1 is going to get a lot of torque because sine 90 is 1. F2 is going to get a little bit less torque than F1 because sine of 45 degrees, let's say, is root 2 over 2, so less than 1. So the torque will scale with the relationship between the r vector and the f vector. Their direction really matters. Okay, so that's the first thing. So here, and I guess I could summarize by saying that here, the torque caused by the first force, that's greater than the torque caused by the second force, which is greater than the torque caused by the third force. And that one's equal to 0 because the force is pulling straight outwards from the axis. What really matters is kind of perpendicular action here. So another way to think about what this expression is saying is that if I imagined a triangle, so if I have an R, let's see, get my colors right. So let's say I have an R vector here, let's say, and then I have a F vector here, let's say. Okay, what I'm really doing with an expression like this is I'm asking, like, how much of the force vector is perpendicular to this R vector? One way to conceptualize that is to say, okay, I've got an angle here. If I imagine dropping down a little perpendicular to the R vector, little right triangle here, the part of this force that's going to cause torque is this length right there. And that is F sine theta. So when I calculate the magnitude of the torque this way, then I'm asking how much of the force is perpendicular to the R vector, and then multiplying that by the R vector. Another way to conceptualize it is in terms of projecting R onto the force. So I could imagine doing a similar thing where I take R and I make a drop a perpendicular down to the force. And then it's really the kind of the perpendicular distance that matters. But I'll leave it with this sort of interpretation here for now. So it's the perpendicular force that really matters for the torque. Okay, so that's about magnitude. But what about direction? So what about direction of torque? This can get tricky, and this is one of the least intuitive things here. To talk about the direction of torque, I'm going to show you a picture of my hand, and hopefully it will make sense when I actually show it to you. So give me a second to pull that up. Okay, so here's a picture of my hand. I've got it laid out flat. You can imagine my thumb points perpendicularly to my other fingers, even though that's not exactly true, but it's approximately true. And we're going to assume that it's true for this example. So we've got torque equal to R cross F. In any cross product, torque's perpendicular to both R and F. So the way you figure out which way torque points, imagine you have an R vector. Your thumb points in the direction of R when it's laid out flat like this. So I'll draw that like so. So your thumb, let's say it's going perpendicular this way, R, that way. Your index finger, or all your fingers in the picture that I've got my hand, as I've got my hand here, your index finger points in the direction of the perpendicular part of the force to the R vector. So that important part of the force that's perpendicular to the R vector, that's the direction that your fingers point in. So F would go that way. And now when you've got your hand arranged in this orientation, the torque will come out of your palm. So your palm will face in the direction of the torque. In this case, that would mean that if I had an R going this way and an F going this way, the torque would come out of the screen in this case. And I'm going to draw that this way. So the torque would go out of my palm. And the way to represent a vector coming out of the screen is with a circle and a dot. And so this is meant to be, if you imagine an arrow coming out of the screen, this is the tip of the arrow coming out at you. So you're just seeing the tip of the arrow. And let me pause for a moment to make a note of this. So this symbol means out of the page, or out of the screen in this case. This symbol means into the page. And the way to imagine what this is these are the tail feathers of the arrow that you're looking at. So you're looking at the back of the arrow pointing away from you here. So out of the page, circle dot, into the page, circle X. Okay, so in this case, so that's the right-hand rule. And we can see how to apply it in our case from before. We have R this way, and let's take F1 as an example. So put your thumb along R, put your index finger along F1, and your palm should face in the direction of the torque. And if you want to take a minute to work that out, try to figure out how to organize your hand to make that work, you can pause the video before I tell you which way it goes. In this case, the torque is going to go into the page. So the torque will go into the page from the first force here. Opposite of what we had in the picture above, just because when you orient your hand according to the rules, sometimes your hand will face in different directions. And in fact, we'll get the same direction of torque for F2, and you can check that for yourself if you want. The key is just to put your index finger along the perpendicular component of the force. F3, there is no torque, so there's really no direction for the torque vector there. Okay, now I want to do a more quantitative example where we put together both magnitude and direction for torque and use this concept of net torque. So give me a second to pull up that example. All right, so I've got an example problem here. Imagine that I have a disk and it is rotating about its center. So that black dot represents an axis about which it's rotating. And the question is, how much net torque acts on the disk and in what direction? Okay, so I've got magnitudes of my forces, and to get the net torque, I want to figure out how much individual torque each force applies and then sum that up. Okay, so let's look at torque 1 first. So torque, the magnitude of the first torque would be equal to R1, F1, magnitudes, times sine of the angle between them. We'll call that theta 1. So if we look at this, R1 magnitude is 0.5 meters. The magnitude of F1 is 10, as given. And the angle between them is 90 degrees. F1 is completely perpendicular to R. So I'll put sine of 90 here. So sine of 90 is 1. So So I just get 5 Newton meters here for the first torque. For the second torque, same thing. So magnitude of R2, magnitude F2, and then sine of the angle between them as well. Well, in this case, I got 0.4 meters is the magnitude of R2. The magnitude of the force is 20 newtons. And then the sine of the angle between them. So what angle should we use? If we look at this, really the perpendicular part is the perpendicular part if we look at the diagram, the R vector points this way for the second force. And so the angle between the force and the R vector is really this angle. Another way to think about that is that if we look at this triangle here, the perpendicular part of that force is this length of the triangle. So it's really, in this 30-degree triangle case, it's the adjacent side. So we can think of this two ways. One way is to say that if R goes that way and angle between, then that makes the angle between R and the force 60 degrees. So we would use sine 60. Another way to think about it is just to use this 30-degree angle and to say that it's really the adjacent side of that triangle that we care about. And so we could use cosine 30, just reasoning out that the perpendicular part will be F cos 30. But either way, we're going to get the same thing because sine 60 and cos 30 are the same. So I'll just put sine 60 in here just to be consistent with our usage of sine. Sine 60 is root 3 over 2, I think. And if we plug all that in, we're going to get 6.93 Newton meters about. Okay, but how do we know whether we should add or subtract these? And how do we know whether we're going to get positive or negative here? We need to use our right-hand rule to figure out the direction of both of these torques. So for the first torque, our R vector goes up, our F vector goes to the right. So put your thumb along the R vector, put your index finger along the force vector. And if you want to take a second to figure out which direction the torque should go, you can pause your video. Okay, in this case, the torque vector for the first one goes into the screen. And let's do the same thing for the second vector. So thumb along the radius vector, position vector, index fingers along the perpendicular part of the force, and palm points in the direction of the torque. If you want a second, you can pause your video. In this case, the torque goes out of the screen. Okay, so that means that if we want the net torque, we can say the net torque is equal to 1.93 Newton meters out of the screen, taking the difference between those individual torques. Okay, what does this mean? What does it mean that the torque is out of the screen in this context? One way to think about the meaning of this direction physically is that the direction of the torque specifies the axis about which the torque is causing acceleration. So we said that net torque causes angular acceleration about the axis, which is the direction that the torque points. So how should I say this? The net torque causes angular acceleration about the axis along which it points. So imagine now that the direction of the net torque, which comes out of the page, is actually just an arrow along this axis of rotation here. And that's telling you that this disk is going to rotate about that. And it's going to rotate counterclockwise in this case. Out of the screen torque here means counterclockwise rotation. Into the screen would mean clockwise rotation. And perhaps it's easy to see why from just understanding these forces and what direction their torque was. F1 caused torque into the screen. That's got to mean that into the screen is meaning rotation clockwise. And our second our second force caused torque out of the screen. Intuitively, that means out of the screen corresponds to rotation going counterclockwise. So overall, we get this counterclockwise rotation with this as the magnitude of the net torque. This way of thinking about the direction of angular vectors as pointing along an axis about which they're acting is going to be really important, and the most intuitive way to think through the meaning of the direction of angular quantities. We can keep talking about that as we go, but I hope this video was useful to introduce torque, and I'll see you all soon. Bye.